So welcome to this presentation. I'd like to start by showing a recent example of deep learning research. It's this topic of generating images from text. That's not exactly language models yet, but you'll see in a second how that fits into the picture. And the work is from OpenAI. The function they try to model is a function that maps text to images. So here are some examples of inputs and outputs of the model they developed. This is here a text prompt, like an armchair in the shape of an avocado. And what the model outputs is images like that. So they satisfy the text prompt in some way. And here's a second example of that kind, also from that model, which just says the exact same cat on the top as a sketch on the bottom. And again, the model outputs something that seems sensible for that text prompt. And yeah, what I find interesting about this is it's one of these examples where you think, if you take a step back and try to appreciate the complexity of the function that's being approximated here, like mapping text to images that match, it's actually really complex. Like if you think back, there was times where people thought if a computer can beat humans at chess, then this mustn't be a really smart thing. And imagine at that time you had told people, you know, we'll have a model that can convert a text prompt like that into images that satisfy this completely well. They would say this needs to be a really intelligent system. And now things like that are possible. So this is from January this year. And one might then wonder, how is it working? And if you look a bit into the paper and the inner workings of this model, it's unsurprisingly, again, a transformer architecture that's behind it. And this particular model has 12 billion parameters and was trained on a huge data set of 250 million text image pairs. And with this specification, the research project kind of fits into a recent development where a lot of astonishing work is being done with transformer models. And I like to think of this a bit as a paper DAG. That's also the image you might have seen on the meetup page already. It's just an idea of visualizing the research that has happened in the field. DALI now being one of the leaf nodes in this directed acyclic graph down here. That's the name of the work I've shown on the previous slide. And in between being a lot of research that was done, and that is mostly based on the transformer paper, the Attention is All You Need paper. So I think with that development, there's some justification for saying, let's take a look at this recent ongoing research that has happened in the past 3 years. So the transformers from 2017, from late 2017, and dissect it a little bit. And that's exactly what this talk is about. So it's, as you have said, it's called a brief overview of the success story of large language models. And the way we're going to go through this is looking a little bit at this root node in the paper DAG, the transformer, and explain on a high level how it works. And then look at the two most important, as I would call them, like children, BERT and GPT. And then all the follow-up research that was done on top of them to the right here in the DAG, and try to cluster this a little bit and make a sense of like the different research directions that have emerged on top of them and that are being maybe also relevant in the future. Yeah, so what you cannot expect from this presentation is like low-level details of the individual papers. I think it's always hard to convey this type of information, even though it's probably the most interesting, actually. It's hard to convey it to a heterogeneous audience. That's just in the nature of sharing knowledge. Yeah, so that's why it's going to stay a little bit on a high level, but there will be like lots of references to interesting papers that you can delve into afterwards. Yeah, and maybe briefly about myself as well. So I created this talk while I was working at Zalando. Zalando has a really active internal data science community. And I was giving this talk internally. And then we have our weekly paper discussion. And in the paper discussion, we were also talking a little bit about large language models. And then this idea came up that this could be just also turned into a public talk as well. Zalando was fine with it, which I'm really grateful. And yeah, that's basically the background here. One thing also about the questions, so Gregor already said it, you can share them in the chat. I think like for this type of talk, when we do it remotely because of our favorite virus that's active right now, then the question is actually what's the benefit, or why is not everybody watching a YouTube video? And I would really appreciate it if people could just share also thoughts they have when they see something. Say, okay, this is matching well with work that I'm doing right now, or you know, any type of thoughts that you have. I'd really appreciate if you share them. This makes it more interactive and actually makes this valuable to have like a session like this and not watch a recording. Okay, so the root node in this paper deck is the transformer paper. The attention is all you need paper, and it has over 16,000 citations by now, which makes it probably one of the most influential deep learning papers ever published. And what it did essentially was proposing a new architecture for sequence-to-sequence modeling, more specifically for translation tasks. Yeah, it was published, or it was developed by Google Brain. The first author is Vaswani. And what one would have previously used in that context, typically for sequence-to-sequence modeling, would have been at that time Lstms. So typical example for sequence-to-sequence would be a translation task. You can see it here at the bottom. This is like a sketch of the model architecture for the Lstm, for the precursor of the transformer, essentially. Where for the translation, you would take a source sentence, like, how are you, and then translate it to the target language. We get a steer. And this is what the sequence-to-sequence models could do. It's one potential use case. And we're first going to take a look at the Lstms briefly, and then to see them juxtaposed to the transformer. And for the Lstm case, the way an input sequence would be processed is that you would sequentially read it token by token. So you'd read the first word and then process it with that Lstm cell, and then pass the state on to the next cell, to the same cell at the next time step in the sequence. So you process the next word here R and take the previous internal representation into account. That's exactly what makes it a recurrent neural network, the recurrence. And the way you would represent the words commonly is through word embeddings. So they could either be learned from scratch here, or you could use some pre-trained word embeddings like word2vec. This was kind of like the standard way of tackling these types of tasks at this time. Yeah, and one of the problems with it is that you have O of n forward passes, where n is the sequence length. That means for every position in that sequence, you need to do an entire pass through the model here, the model being like this blue cell, and that makes it slow. Yeah, and what the transformer introduced was removing this recurrence and replacing it by attention. And attention is this cool mechanism that makes it work so well, and that makes it possible to process an entire sequence in a single forward pass through the model, instead of having to do this recurrently. And that just speeds up the training a lot. And at the same time, it turns out to have like some favorable properties, like not having to deal with the vanishing gradient problems, yeah, these types of things. It's also important to note actually here for the generation, when you generate something, that you still need to have O of n forward passes during inference, but during training, you can also train in O of 1 forward passes. So this makes it really fast for training. Yeah, and on a high level, it's again the same structure. You have an encoder on the left-hand side and a decoder on the right-hand side. Maybe we can actually go through it quickly. So it's the same setup here. We have inputs, and here's the outputs, like in the target language, a sentence. And in this case, the inputs are not being processed sequentially, but every position has access to every other position as indicated by these arrows between the blocks. And that way, the entire sequence is processed, and then hidden representation with the length of the sequence is being made available to the decoder over here. And the decoder can then generate its outputs. Yeah, for the details of how the attention works and the inner workings, as I said before, this is not a part of this talk, but for this, I would recommend this blog post. There are many blog posts on this topic. I think this one is a particularly well-written one. It's called The Annotated Transformers by Howard NLP, and it goes through the paper step by step, implements it. And I think seeing it in the code form makes this really accessible. Yeah, so this recommendation I want to give you on the way. So what to take away from here for the transformer, speeds up the training process a lot and has some favorable training properties. And that just made it much more successful than in the Lstm. And as for the architecture, I want you to take away that it consists of these two parts, the encoder and the decoder. And now if we descend in the paper deck that we've shown before, that was the transformer, the root node, then the next paper that was published, which I deem influential, is called GPT. And GPT stands for Generative Pre-Training. Now, the idea of GPT is to take only a part of the transformer architecture, namely the decoder, that's here, the entire transformer architecture, and what GPT is using is marked by this red rectangle. And it just takes it as is, so it's not introducing a new architecture in any way, but it changes the training objective. Remember in the transform paper, the training objective was sequence-to-sequence modeling, so they had some translation examples like a tuple, source sentence, target sentence. And in this case, we don't do this anymore. All we have is a large corpus of language without any labels, and that we try to model. Yeah, we'll talk about this in more detail in a second. The paper is from OpenAI from 2018, so it was published just shortly after the transformer. Yeah, and now the way GPT is working is that it also processes, like the transformer decoder did, processes its inputs sequentially during inference and in parallel during training. And you can think of this like, if you try to model language with it, the way you would do this is that you take a part of the language, like a prefix over here, and then the model is going to output something that it expects to follow that prefix in normal, natural language. So the model tries to continue something based on what it saw in the training data. And all you train it on is exactly the same task. You take training data, take a large sentence, split it, say this is my context to the left, what is to the right of it is the continuation, and the model's task is to predict exactly this context, that is continuation based on the context. As some example, just some sentence, here comes the sun, and then the model would continue the smiles returning to the faces. This could be one example, or in any way you could use it to continue some sentence. And the cool thing about it is that for training it, you don't need these tuples anymore of labeled examples, source and target. You can just use any large text corpus that contains natural language. So what's changing is, I'm repeating myself, but this is the key, like it's not the architecture, but it's the training objective. And this is now language modeling, generating language. So what do they do concretely in the GPT paper? They gather these large amounts of training data that I talked about, this large text corpus. Where could you get it? You could go, for example, to Reddit and then just scrape it from there, or follow like outbound links on Reddit and then scrape these web pages, or you go to Wikipedia or get some book data set, this type of natural language. So really just large corpora of language. You take them, then you train this model on this language modeling objective that I mentioned. So you take a part of the text and let the model continue it, and that's its objective. And once you've trained the model on that objective for a long time, remember, like we have really large amounts of training data, you probably want to train it for quite some time, so it really picks up all the subtleties of human language. So once you've trained it on this, then you can use it for inference. And you have this prefix model continuation setup. And now during inference, you can choose your own prefix and put anything in there that you like, and the model is going to continue for you. So now you could say, I just put as an input into the model some question. This is a screenshot from the GPT paper. So a question you might ask is, who wrote the book, The Origin of Species? And then the model is going to continue how it would expect normal natural language to continue in that case. And an answer it might give in that for that specific question is going to be Charles Darwin, because that's what it has seen in the context of this question. And the idea is that not every question it sees in there, not every question that you ask it, it needs to have previously seen. That's this idea of generalization that's happening. Yeah. So now you can go ahead and instead of asking like these very simple questions, which have like these answers, which are just two words or so, or here it's also a year. And you could also go and ask more complicated questions, or in the prefix language, you can put more complicated prefixes into your model and see what the model continues with. And that way you can use a language model whose only capability is to continue something that you give it and use it for a wide range of different tasks. And the different tasks are listed here. So one might be question answering. This is the one I just showed. So you put maybe some text with information into the model as a context and then write a question, then see what the model generates, and this you take as the answer to your question. Or another application would be text summarization. And for this, they just had this idea of putting a text as a context into the model, and then placing a TLDR behind it. And then the model knows from the internet, because that's common on Reddit, that you have a TLDR and then a summary afterwards, that it's now asked to write a summary. So it's going to continue with a short summary of the text. Yeah, I think this is really like amazing what capabilities are in there only after seeing natural language for a long time, because the natural language contains a lot of these tasks already, and that way the model, yeah, is suitable for them as well. Other ones are story generation. You just put some text there, a story, the model continues it for you. Or you can even use it for translation. So they would say, give it some text and then just continue with in English, and the model is going to output in English. Of course, that's not always working so well. And in reality, in the paper, you'll see there's like a couple more details to it, but that's the rough idea. Yeah, so GPT can, I'll just summarize this again briefly. It looks at large amounts of text, natural language, and then it's suddenly able to solve a range of tasks, because natural language is in and of itself, if you model it well, really rich. And then GPT also, because it generates nice texts, it became kind of famous also in popular science, made it into the news, for example, in The Guardian, which published an article where they said GPT wrote this entire article. How would this work? So you just write the beginning of the article and then see what the model continues it with. And that's then an article written by the model. That's technically correct. In reality, they've used some tricks there, like putting a couple of more contexts in between. So the model wouldn't need to generate the entire article in one run, but would generate a part, and then they would write the continuation and the model would generate more, sort of like that. But, you know, this made it into the news, and it's also to some extent justified, yeah. I think so. The link to this article is up here. I've put it into the slides. So going back to the paper deck, we looked a bit at the transformer first, and then its first descendant, GPT. And now it's time for the second descendant, called BERT. BERT stands for Bidirectional Encoder Representations from Transformers. And that's another one of these papers that gets cited like ridiculously much. Here it has already 15,000 citations, and this paper is from 2018. So it's an extremely popular paper that's also easy to read. And similar to GPT, it is largely based on a transformer. In fact, it's using, just like GPT, a part of the transformer architecture, and only introduces a new training task. So you saw, like, again, here's the entire transformer architecture. Previously with GPT, we've been using the decoder on the right-hand side, and now BERT, marked with the red rectangle, is using the encoder. The encoder's task originally, if you recall, the translation task was to convert the source sentence into some representation that's helpful for the decoder so it can translate it. Now they only take the encoder, and so they need to have a new task for it because there's no more decoder which could steer it during the training. Yeah, and the task they introduced is called masked language modeling, and this we're going to also talk about in a second. So BERT is another paper from Google that was, yeah, as I said, in 2018 published. And it's actually funny, Devlin is the first author, and he was giving a talk in Berlin a while ago, which I attended with some colleagues, and it was cool because he talked a bit about the, you know, things around developing a paper or writing, doing research like that. And he was telling us that he came up with this idea, and he was working on the Google search feature for smart responses. Maybe you know this, and sometimes a text, like a box, is popping up, and this one shows like a smart response instead of just listing web pages. And this was the context in which he, as a software engineer, actually came up with this model, which is now so popular in the deep learning community. And also he shared with us that the BERT model itself, they would never deploy in production for search because it's just too costly. That I also found like an interesting detail he gave away in his talk in Berlin. So on to the objective that the encoder is being trained with, the masked language modeling. This works a bit different now than the generative objective that we saw before for GPT. The objective here is, given a sentence in which you remove a single position, in this case the word in the middle is being removed, R is being replaced with a mask. The objective of the BERT model is to predict which word was removed from the sentence. And all information it has available in order to solve this task is the context. That's like the words to the left and to the right of that masked out word, and all its prior knowledge, like all it has seen before in text. So you can tell, here are some examples, like I play the, and then you can plug in some word. Or my brother likes, maybe he would fit his basketball. And you can already tell if you want to fill in this word correctly. You need to know that for brother, you would use his and not her, for example. So filling these words requires some knowledge. How is this working internally? So the inputs, actually, we can go a bit into detail here, I think. The inputs, they're being embedded through a learnable embedding. That's usually, so one problem you might have in reality, if you want to break all kinds of words and you have like a large corpus, is that you don't just have 20,000 words, but you have like 400,000 words because of typos and whatnot, and names and so on. So what you do in reality is split into word pieces, into the largest word piece that you can split a word into. So most words you are going to embed directly as they are, but in particular the long ones, maybe also words from another language, you're going to embed as their individual pieces. And then you have typically like 40,000 different tokens that you feed into the model, and they have this learnable embedding here then. And then the model is internally processing the entire sequence and has access to every position. And its objective is then to model a distribution at the softmax here over all the symbols in that 40,000 token dictionary. And this distribution, the objective then is to minimize the cross entropy between this distribution and the ground truth. So the ground truth being the word that was masked out, in this case R, and that's what the model is being trained on. And an interesting property of this is also that the softmax has a really easy time modeling ambiguity. So if in your data you see words like I play the, and then you see like many occurrences of that particular sequence, and the following word is ambiguous naturally, because you might have some people who play the flute, or some people play the violin, who knows? And this ambiguity, the model can explicitly model through the softmax by assigning the correct probability mass to these different tokens that are possible in that position. Yeah, so modeling this ambiguity is another big strength of all the transformer-based models. Like, in which case, maybe you might wonder, in which case would you not be able to model this ambiguity? Well, if you wanted to predict a word-to-vec vector, for example, there's no way for you to say 50% that this is king, 20% that this is queen, and 5%, I don't know, like this is some other word in the embedding space, because you cannot predict a vector that's exactly positioned between all these vectors at that, so they have like the percentages assigned to them. So if you predict a single dense vector in an embedding space, you wouldn't be able to model its ambiguity as you can with the softmax. Hope that made sense, yeah. Otherwise, we can happy to talk about this in the Q&A as well. Yeah, and now what would you typically do if you have a BERT model? Well, you can train it on this task, and then you have this capability of filling in a missing word in a sentence. But what people usually do is use these internal representation that the model uses itself to solve the pre-training task, the masked language modeling, and use these internal representations for another task. So you might want to use these as rich word embeddings, which tell you something about the meaning of the particular word in the sentence, so in its context. That's in strong contrast to word-to-vec, for example, where you assign a static vector to every word in every situation. And with BERT, you would have a vector that's context-dependent, which reflects the word that the word's meaning in that particular sentence, given the left and right context. Yeah, so some applications that BERT would be used for is then text classification as one example. Now to map quickly between the figure that we see here and the figure we saw on the previous slide. On the previous slide, we saw the inner workings of this blue box, and now we just see inputs and outputs. And outputs are not the predictions anymore, but these internal representations, the one I marked with the red circle on the previous slide. And now you have this possibility to also extract a single representation that reflects the semantics of the entire sentence. And this one you could just feed into a linear classifier and would be helpful for solving a text classification task. Another thing you could do with BERT is named entity recognition. In that case, you would use the representations of every single one of these tokens in the sentence, and then again feed it through a classifier. Can just be a linear one, and it's going to tell you the classes of these. And this is then again not a masked language modeling task anymore. This one you do first, then you get the trained BERT model, and then you use the rich semantic vectors and then train it supervised on some named entity recognition or text classification task. Yeah, and then similarly, you can do sentence equivalence, give it 2 sentences, let the model tell whether they're equivalent or not. Question answering you would not do in the GPT fashion that you generate the answer, but that you provide a list of answers and the model's task is to rank them. This type of approach. And sentiment analysis is just text classification, but so common that it deserves its bullet point. Yeah, so one of the things I also promised in the abstract of the presentation is that we're going to talk a bit about why the models work so well and develop an intuition for this. And here are some examples of the masked language modeling tasks that illustrate why a model that is able to solve this task well is necessarily having some understanding. Defining understanding is hard, but is having some understanding of our world. I had this basic example before, how mask you, and then the solution was R. It's fairly obvious. If we look at a more elaborate example, this would be the mask chases the mask in the savannah. You know, you can think for yourself what fits. You know, who chases whom in the savannah. That already requires some domain knowledge. You need to know that animals probably chase each other, or humans can chase each other, and like which animals live in the savannah and so on. So in this case, it's more likely that lions or cheetahs chase antelopes or wild beasts. This is a cheetah. And that cats and mice, for example, wouldn't fit here because they don't live in the savannah. And it's just one example which shows you if you have a model which is able to solve this task really well, which BERT is, because you have a large amount of data that you can train it on. You have a model that's able, the transformer, as I said, is really efficient to be trained. So you can have a high capacity model, large amount of data. You can have a model converge on this task to some extent. And it's going to be able to solve it well. And you can see how much knowledge it actually requires to be able to do that. And this is exactly the knowledge that, I mean, the output is being computed here in the softmax. So this is exactly the knowledge that is contained in the vector that the model uses internally at that position. This contextualized vector that I said you could probably use in your downstream tasks. Yeah. So saying it in one sentence, that's the first bullet point. Solving it requires common sense and knowledge. Yeah, I maybe find also important to point out that this is really being enabled by the transformer architecture, which is able to process these large amounts of data. Okay, good. One aspect I want to talk about quickly is model open sourcing. This is a screenshot from Reddit, which has 600 upvotes, which is quite a bit on the machine learning subreddit. And someone was saying, let's have a discussion about whether OpenAI should change their name to Closed AI. Yeah, and this was because at that time, OpenAI had the best language model, the GPT model, and they decided not to open source it. It's like a 1.5 billion parameter model. So it's nothing everybody can just train by themselves. And I find it a really nice move from OpenAI to not open source it. It goes a little bit against the common opinion, but I think the discussion they sparked with it was really good. And they had their own stance. I'm putting the link here on why they wouldn't want to open source it. They said it could be used for malicious purposes and so on. But I think what was great about it was that it sparked a large discussion. Eventually, they open sourced it because research just advanced, and their model at some point is not even that relevant anymore. But I think the discussion they sparked is really valuable. What harm does it do to open source these language models? And it also shows that having a language model is some sort of value. Yeah, I said the model has 1.5 billion parameters, so training it costs like $80,000. Yeah, it's not to be underestimated what costs so much about it. This is the computing power, because you need to keep a couple of GPUs occupied for a week or so, and that's just not going to happen for free. The number, the 80,000, I have from this reference cost. All the references always put in these uppercase spelling. And yeah, they have a lot of interesting information actually on the cost of different language models, on the cost of the attentions. All you need paper is often just estimated, of course, but it gives you an idea of what crazy things are going on there, and that a language model is nothing that a company can immediately train for themselves unless they have some money available. Typically, language models now, like you can just download for English and German and everything. You can just download them, but it gets interesting as soon as you want to train it on your own domain-specific corpus. Then it gets expensive because then you can't rely on the one that another big company has open sourced. So to conclude this first part of the presentation, which was about GPT and BERT, I have this overview slide, which compares the 3 different models, or let's say 3 different approaches to training. The Transformer first one that introduced the architecture, and GPT and BERT that use it in 2 different ways. So what are they using? Yeah, Transformer introduces this encoder-decoder structure that's based on attention. Encoder-decoder was previously common, Lstm and so on, but now they do it with attention inside. Then GPT just takes the decoder and uses it to generate text. BERT uses the encoder and doesn't generate text. Yeah, typical application is hard to say because in the meantime, everything is being used for every application. Like BERT is being used to generate text as well. And there's like, this is the BERT has a mouth and it must speak paper. So it's kind of, yeah, take it with a grain of salt. It's the original application, Transformer for translation, GPT for text generation, and BERT essentially for retrieving these vectors that capture a word in its context for downstream tasks. Yeah, and lastly, the objective I already mentioned partly. Transformer has the generation in the decoder, GPT kind of the same, and then BERT, it's masked language modeling, where you remove BERT and the model tries to predict it. Okay, so for the second part of the presentation, I want to talk about the nodes in the paper deck that are descendants of BERT and GPT. And I clustered them a little bit into different research directions that I consider relevant. That's, of course, very subjective. Like, it's not possible to read all the papers that were written on top of them, and clustering that depends on your own preferences. So this is kind of my view on this emerging research here. Whoops, yeah. So one thing that has happened is that companies and people kept on upscaling these models. The BERT paper originally had this base model with 110 degrees of freedom and parameters, as we call it. And later in GPT, the number of parameters, GPT was actually published, like there are 3 different GPT papers, yeah. And they changed the parameter count over time. The first one was in the range of BERT with 117 million parameters. Then the second one already had 1.5 billion. And the third one, this is the most recent one, that has 175 billion parameters. That also explains the cost. Yeah, the switch transformer is the largest, I think the largest model that was ever trained, as far as I know. It has 1.6 trillion parameters, which is just madness. There's also a Google paper, and the way it works in practice is that they split the model into a couple of parts, and then which one they actually use is being decided in the beginning. It's like a mixture of experts sort of thing. That's how they get to this super large number. And the cost estimated for the switch transformer is greater than $1 million to train this model. This is complete madness, yeah. An open question here is also, oh, okay, let's look first at this plot maybe. The plot is showing the model performance aggregated across a couple of benchmarks, plotted against the number of parameters that the language model has. Yeah, and be aware, it's like a logarithmic scale. And here we have the 175 billion, which is GPT-3, the figures from GPT. And you can see that there's no saturation that we see in the performance on the downstream tasks. So given this plot, we would expect that adding even more parameters makes our performance on downstream tasks even better. And this is an interesting observation because it means we haven't hit the ceiling yet. And it also shows that we don't have overfitting problems here. Jetzt wieder besser. Wait, who is it? Okay. Yeah, that we don't have overfitting problems yet. And that's an interesting dynamic. That's the reality, that we have models that have so many parameters and still don't overfit, which is an unsolved mystery in deep learning, one could say. Okay, after the larger language models, there's also the direction of having smaller models. I took this table from a paper that's called Primer in BERTology. It's a really good overview. It's about a year old, I think, so it's starting to be outdated. Yeah, this is already 25% of more than of BERT's lifetime are already past the paper's publication. So the progress is extremely fast in this field. But nonetheless, it's an interesting table for understanding how smaller models, what motivates them and what one does with them. And I would first look at the different columns in the table. They're highlighted in red again by this rectangle. And they say among which dimensions one would compare a model size reduction method. So the first one is the compression factor. By how much do you reduce the model size with your method? Then the second one is how much of the original performance you're able to retain as close as possible to 100% ideally. Yeah? And then the speed up that you gain from your compression. This guy has like a lot of speed up, or this one. Yeah. And along the different rows that are grouped in this paper, we can see the different kind of clusters of methods for model size reduction. And the first one is distillation, which is basically this idea of having a large model trained and then training a smaller model, which has the task to imitate the behavior of the larger model. So that's the distillation. The other one is the quantization. For the quantization, you would just reduce the precision of the internal representations of the model, convert your float 32 to float 16, for example. Probably some more sophisticated methods, but along those lines. And then pruning, as the third one here, is removing parts of the model. That's the idea here. So you might identify that certain layers or attention heads in the transformer. I didn't mention what attention heads are, but think of it as a component of the attention mechanism. And that you might notice some of them are not contributing to your downstream task performance. So you can just as well remove them without seeing any impact. And these pruning methods are about identifying such parts and then removing them. And for other, this is just like comparable architectures that are kind of similar, but probably more expressive. That's how somebody gets a, gets, I think, this performance improvement. Actually, now that I look at it, the compression is smaller than 1. So yeah, okay, never mind this part. This is a new architecture, BERT, that's modifying the transformer a little bit. Okay, another thing that's relevant are the benchmarks for using these models. Like absolute standards are the two benchmark suits, glue and superglue. They contain a range of different tasks, and one typically evaluates the model on all of them and then just reports the performance on the individual tasks and the mean performance. And this tells you roughly how good your model is. Yeah, and the idea was with glue, like glue was the benchmark, I think, for a longer period of time. And then the models exceeded the human performance on it. And as soon as that happens, it's a bit tricky because you don't know how helpful the benchmark is anymore, because it might be that you hit the optimum that's possible at some point. So it's always good to have the humans be better than the model. That's why super glue got introduced. It was called the stickier benchmark, in hope that the benchmark would be useful for longer, but it also got actually cracked relatively quickly. And one of the problems one sees with language models that one would ideally like to benchmark is their reasoning. If you ask a language model what the color of a sheep is, then it's going to tell you it's black. And that is because the language model doesn't have an understanding of the world as we do, but it just tries to model what we write down in language. And what we write down in language doesn't necessarily reflect what's going on in reality. For example, in English, black sheep occurs 25 times more often than white sheep in the English corpora. So naturally, the model is going to pick that up and it's going to think that this is the true color of sheep. In other languages, not so bad. In Korean, for example, I have the number here. It's like in Korean, the black sheep are 1 to 1.5. So white sheep are occurring 1.5 times more often. In that language, it's not so common to use this idiom. Yeah, but the message I want to say with the black sheep is that one needs to be aware of the fact that the language models, even though they look smart and people might think, oh, it's really frightening, they write a news article, that all they do is imitating our language and interpolating in between. And this is quickly hitting limits if you would try to ask the model to solve more complicated tasks, like asking it what the color of sheep is. Yeah, in this blog post that I put here, they talk a little bit about this, because this you can go further with, and you can say, in our language we typically associate certain jobs with certain genders, and this is something that our society has recently started to dislike. So this is something we don't want our models to do. And these types of problems you have with language models. That's also something that the called the parrot paper. It's called like stochastic parrots, and that this paper criticizes. Now I'm jumping a little bit, so we're at the bottom of the slide. It says essentially the language models reflect the data they were trained on, and the people who train language models, they care very little about the data, and they should care more about it. They should look more into which biases there are in the data, and should think about methods for removing these biases. Because otherwise our language models are stochastic parrots. They just repeat what they see in the data. They're going to pick up these biases, and this is not going to help us as a society eliminate them. And the second thing the stochastic parrot paper criticizes is that the CO2 emissions of training language models are really high. Like I said before, for the switch transformer, the cost was probably like more than $1 million US. And you can think, if you keep GPUs running for so long that your expenses run into the millions, then you're using a lot of electricity. And electricity is, at least partly, not coming from clean energy sources, and that leads to these CO2 emissions. So I'm quoting from the paper, from the stochastic parrot paper, and where they say a human is typically emitting 5 tons of CO2 per year, and the transformer big with architecture search, it's an important thing to add, otherwise it would be a bit surprising, has probably emitted around 284 tons of CO2. I added for comparison that a space shuttle launch emitted like 4,600 tons of CO2. So I think it's important to be aware of these numbers, and then how to decide based on them. This is a question of values, in my opinion. This is a question of like whether we say research, which these language models are, or the space shuttle is worth it for us to do that harm to the environment or not. Yeah, so this paper was written by Timo Denk. This was in the news like big times in a few months ago, because she got fired for the paper, and is, I think, now at some university, and they published it anyway. But yeah, there was a bit of tumult in the news, in the machine learning news, let's say. Yeah, and actually about the biases, I want to add one more thing. I said the models reflect the data they were trained on, and what data they're typically being trained on, I previously also mentioned, that's Reddit and Wikipedia. Now both Reddit and Wikipedia have as a majority male users. Now on Wikipedia, there are 15% female contributors, and on Reddit, there's like, at least in the US, 64% men. And yeah, most of them are also young. So you're naturally not going to reflect the mean of the society if that is what you wanted. You don't get it that way. Another direction of research is to look into the models and try to understand what's going on inside. I previously did not explain what attention is exactly. So in this case, just think of it as a way of different positions in the sequence, looking at other positions. This is what these blue lines are indicating here. Yeah, and what people would do is look into the model and see by which part of the sequence an internal representation is being most influenced on. So you could say, my embedding of, I don't know, the mechanic is being influenced by some word, some adjective that's in front of it, like these types of things. So they try to understand what the model looks at in order to compute its internal representation. That's the what does BERT look at paper. That's one of the, if you're interested in this topic, like looking into the inner workings of the model, I think this is the go-to paper. The second one, What Does BERT Look At, has been cited like 500 times by now. It's really one of the important ones in that direction, or at least one of the more much cited ones. And the other one is the Picking BERT's Brain. This is more, maybe you remember from Word2Vec, people do this fun stuff and take like queen, subtract female, and then add male or so, and then they end up in proximity to king. And this type of thinking you can similarly do with contextualized embeddings as well. And that's what they do in the Picking BERT's Brain paper. So they look at the contextual vectors. Yeah. Something also to have heard of is the long-range arena that's in the field of processing long sequences. I only talked about like these really short sequences, how are you so far? And in reality, the maximum sequence length you typically process with a model like BERT would be around 512. So could be shorter, but longer gets hard. And why does it get hard? Because the computational complexity of the attention in both memory and computational complexity is O of n squared. So you quickly hit a limit as you increase the sequence length, but there is still interest from the research community to increase the sequence length, because having a longer sequence length would allow it for you to transfer this model to other tasks. So Google has published this paper called Long Range Arena, in which they define a couple of benchmarks that test models for sequence lengths from 1,000 symbols up to 16,000. And if you were able to process such long sequences well, you could probably work on character level, which is really helpful for dealing with typos and with weird language, as you often have it on the internet, or maybe doing speech processing or image and video processing for these types of applications. That would be really promising. Yeah, and what we see in the figure, that's one of the figures from the Long Range Arena paper, is plotted the performance of the model. So the higher up it is, the better it is. And then the further to the right it is, the better it is, because that's the speed at which it processes the sequences. Here's the transformer. It has a good performance, but it's really slow. That's why it's so far to the left. And here, the rightmost paper, also worth mentioning, is the performer. Yeah, the names are often related to each other. This is something the researchers find funny. And the performer is trying to approximate the attention matrix and saves time that way. It's a really math-heavy paper. Also an interesting one to check out, I think. And very recent, I just added this after giving the talk at Zalando, is the FNet. This was published like 2 weeks ago. And it's a Fourier, it adds a Fourier transformation instead of the attention matrix. So it's a completely different approach. You say the model doesn't need to learn anymore from where to read in the sequence. We just do this with a fixed non-parameterized transformation, and it's also working, and it's like a crazy discovery. It's not performing better in the long range arena yet than the other papers, but the mere fact that it's equivalently like strong is already really surprising, and this maybe opens up a new research direction, which did just the attention again, that has just become so popular. So that's an interesting one to check out. Yeah. And here just I've listed a couple more of these papers, the linformer, linear transformer. These are like a couple of the ones that are all dealing with the same problem, which is process really long sequences with transformers. Yeah, and another example of research that follows up is the transfer to other domains. In this case with AlphaFold, that's like from DeepMind, some research in which they predicted how proteins would fold. That's another example of processing really long sequences. Now, they solved this very important problem, apparently, which I still don't understand what it's actually about. But anyway, another one is applying transformers to images. In this case, normally you always use CNNs if you want to deal with images, but the transformer can deal with images as well. If you just take your image and split it into patches, and suddenly you have a sequence, and the sequence is what the transformer can deal with, and then you can use it for image classification. I don't think that this is going to prevail, but it has been tried, let's say. So now, since I gave this talk at Zalando, I also included some examples from my previous team. At Zalando, we used the transformer, which was, as I said, originally used for translation tasks, and used it to translate a customer's click history into an outfit recommendation for that customer. So you can see actually outfit recommendation as a translation task. And that's a nice example maybe for transferring the transformer to another domain, in this case, recommendation in an online fashion store. And this thing is actually running in production. If you go to the Zalando page, you'll see articles showing up like that. Here's a pair of pants. And as you scroll down, like here's all the details as usual. And as you scroll down, you'll get some outfit inspiration, say style advice. And these are outfits that Zalando has curated itself. And this is an outfit that was being generated, personalized for the customer who's browsing right now by a transformer model. And instead of outputting words in a target sentence, the model is outputting pieces of garment, the clothing that composes the outfit. So I find it for Zalando honestly really impressive that they have like a transformer model like this running in production, because productionizing something like that is, I guess, harder than evaluating it on some glue benchmark. You need to set up like daily retraining, monitoring the performance, the regression over time, all these things, monitor the data quality and stuff, dealing with latency issues. Yeah, and Zalando is doing this. Quite sophisticated, I think. Yeah, and you can browse the outfit in detail and look at it here. Another example from Zalando is outfit completion. Sometimes we have these outfits and one of the articles goes out of stock, and then we want to predict a replacement for an article. And that's exactly what BERT is very well suited for. Here's like the original outfit, and we would just remove the article that's out of stock, and BERT would give us a couple of predictions. And in this research project, the predictions would additionally be conditioned on a customer context, because the outfit itself, maybe with 3 other articles, doesn't provide enough context for you to make a reasonable suggestion for a replacement, so that you get some additional help in making that decision. Yeah, this one is not in production, but still like a research project from Zalando that I want to mention. So transformers have also been used in speech, but not too much. As far as I overlooked this, in speech, the common choice is still CNN. Yeah, and this is already the last slide of the second part here. Just a couple more papers that didn't fit into any of these categories really well, but that I wanted to mention because I think they're interesting. And the first one is this paper about what language models memorize. It's really cool. They try to find out from your training data set which text sequences the model has memorized in its weights. So without any access to the training data set, you want to find out whether some particular text from the trained data set is inside of the model. And they were actually able to extract, for example, pi just from the model weights, like by putting a prompt into the model saying like pi equals 3.14, and then the model continued pi correctly for 824 digits. Like it's real madness, if you ask me, because this is like purely stored in the model weights in some completely strange representation that we cannot read, but the model is able to reproduce that number with such high accuracy. And they do a lot of funny stuff. Like they also find that the model stores some UUIDs, which only appeared like 5 times or so in the training data set. It's really crazy. Yeah, how much is being memorized. Yeah, the second bullet point is about the transfer of transformer modifications across applications. That means they look at a bunch of modifications that were made to the transformer architecture and then evaluate them in their own setup in different applications. And the finding they have mostly is that the modifications don't transfer that well. It's a bit of criticism also to the way the research is being carried out there. Yeah, then the Electra paper is taking an entirely different approach to training the language models. They train them, train them in an encoded, in a generated discriminator setup, similar to GANs. That's another one I think is interesting to check out. And then the fourth one is not a paper itself, but it's a blog post. And this blog post I like very much because it talks about this intuition behind self-supervised learning. The entire thing that we talked about, you take a large corpus and you train your language model to replicate the language that's being used in this corpus, or you take BERT and you mask out the BERT and the model predicts the mask out BERT. These types of things, that's all the self-supervised learning idea. And the blog post is from Facebook. They talk about why they think that self-supervised learning is an enormously powerful approach, which, the results of the papers suggest that. And they give an intuition for why that is and why they think this is actually the dark matter of intelligence. Also reasoning based on humans doing similar things when as toddlers they just perceive things and try to make sense of them. So to wrap this up, I think it's fair to say the transformer-based architectures, the BERT GPT and also the original transformer, they really dominate NLP right now. On the benchmarks, all the good models are transformer-based architectures, and that's a recent development. Yeah, the two most important descendants of the transformer paper, I think, are BERT and GPT, and they both use the same architecture, but modify the training task and use the self-supervised learning in order to learn their internal representations. And a lot of work that's being done is about transferring these success stories from NLP into other domains and making them work there as well. I think one of the big challenges is to add more reasoning to the models. We saw this example of the black sheep that the model gets wrong. And benchmarking this would be the first step. And as soon as you have benchmarks, then the community can implement them and it's going to develop solutions for them. But just benchmarking intelligence and reasoning in general is not an easy thing. On the right-hand side, I've shown another DALL-E example of text prompt and AI-generated images. This was particularly suited in the context of Zalando because we have a team. They have a team which is working on a GAN that's taking a set of articles and renders it onto a fashion model. So the idea is that in the long run, they want you to just say, these 5 articles I have, and now render them onto a body for me, maybe ideally my own body so I can see how it looks on me. And now, there's a completely different approach to saying, I want something rendered on a body, and a model does it for you, which can at the same time do everything else as well. It's pretty crazy. Sounds frightening. And every time somebody is afraid of AI, I also like to show this, what you get if you type into Google, not striped shirts, that the result you get is a lot of striped shirts. And as long as that's the case, I think there's not too much reason to be afraid. So this concludes the presentation. I will try to share the presentation somehow, maybe through the meetup page. And then you can also find all the references there in the appendix. There's like one large slide with all the paper references, and then also the blog post, which I sorted by subjective priority. So I think the ones on the top you should read first. If you want to read just a few, then start maybe with the why self-supervised learning works so well. Yeah, thank you for your attention. Let's go to the Q&A.